Yeah, okay. Is my voice audible to everyone?
Yes, sir.
Yes?
Yes, sir.
Okay, okay. It's clear, right? I mean, there is no breaks or anything, right?
No, sir.
Okay, okay. So let me just share my screen. Yeah. So is my screen visible to everyone?
Yes, sir.
Okay. Mm, right, we'll begin then. So before we begin, I would like to apologize. The thing is, I told by this week I'll somehow prepare that notes for you guys, but due to some commitments in the lab, and because we had the storm last week, it was a very bad storm, so we had no other choice. No, but there was some problem with the equipment here, so I couldn't prepare the notes. Also, there was paper valuation, so I request you guys to wait for one more week so that I can prepare those notes, and also I will upload my PPTs that I'm taking here on the drive so that you can refer to them. So I'll also post questions along with answers in the forthcoming sessions. If you guys have any doubts in those problems, feel free to ask me. So okay, so we'll go to the session. So in our previous class, okay, we saw about other than what is mentioned here, we saw about perovskite structures, like what are perovskite structures, and how are its arrangements, and what are the different perovskite structure, what is the Goldschmidt tolerance factor. So we saw all of these things, and other than that, what did we see? We saw about the hexagonal closed packed structure. So what is the arrangement of the HCP structure, and how do we get the C by A ratio, and how we arrive at the um, volume of a uh, hexagonal unit cell, and then we also arrived at the atomic packing factor, how to find the atomic packing factor of the HCP. So these were some of the things we discussed. Then also we discussed about the theoretical packing factor of a material. So there is the formula, right? So number of atoms times the atomic weight divided by what will come here? Any idea?
VC into NS.
Yeah, PC into N. Sorry, Na, right? So VC is volume of the unit cell, and Na is Avogadro number, right? So we saw about theoretical density. Sorry, sorry, not theoretical packing factor. It's, theoretical density. Okay, just a sec. So we saw about theoretical density, right? Rho. So this gives you the rho. Okay, so we saw about this, and then when we saw the problem, I think we had the power cut, like the Miller indices. We were about to go into Miller indices, then we had the power cut, so we couldn't carry on further. So now we will somehow complete these things. Okay, linear and planar densities of crystal, crystallographic directions, family of directions, and crystal imperfections today. So these were all the things we saw in the previous class. Um, Okay, so the theoretical density we saw, and yeah, we worked out this problem too, right? And now, yeah, we came all the way up to here. Am I correct?
Yes, sir.
Yeah. So any doubts till this, guys? Uh, okay. So I'll proceed. So next, so you guys got to know about these point coordinates, right? So if a particular coordinates like this are given, say 1, 1, 1, or a by 2, b by 2, or 1 by 2, 1 by 2. So you know how to mark the coordinates on the crystal lattice, right? So on the unit cell, right? So
Yes, sir.
yeah, that's good. Yes, yes.
What is the use of the Miller indices?
The unit of uh,
Use of sir, he is asking use of Miller indices.
use. Okay, okay. The use of Miller indices is like if you have to find the crystallographic structure, crystallographic arrangement of a particular crystal lattice, right? So in that case, you will be using Miller indices. Say for example, we have here we saw the different packing sequences, right? For like if for FCC that is ABC. Actually, I'm sorry, I still like haven't found out how this like this is happening. Please give me some more time. And then for HCP, it was like this, right? AB AB. So this sort of sequences we can find out through Miller indices. So if we take a particular crystal, right, and we do something known as the X-ray diffraction, right? So what we will get is we will get certain peaks. Okay, so these peaks can be indexed to a particular Miller indices. Say because see the thing is while doing the X-ray diffraction, okay, we have the sample over here. We have the source which gives the X-ray beams, okay, and then we have the detector, right? So the X-rays come from the source, strike on the sample or specimen, whatever we call it, and then travels to the detector, right? So this source X-ray, this sample will be placed on a rotating table. Okay, so this table will be rotated and at different angles. Okay, at different angles, you will be getting certain peaks. Of this, we will find the prominent peaks. Okay, and from those prominent peaks, we can find out at which particular plane the X-rays bounced off, right? Whether it is the 100 plane or the 111 plane, and from that we will be able to conclude which material it is. So you get my point, right? If we know the Miller indices of a particular material, we will know what that particular material is. So they have these standard data, okay, in some websites, like some standard websites known as the JCPDS and ICCD, sorry, ICCD. So this is International Crystallographic some database. So this is a Japanese crystallographic database. So I do not know the full form, but either it's in JCPDS or ICCD, one in these two formats. So if you would go into this website and if you take a material, say magnesium, right, they will give the XRD peaks. How will the magnesium peaks look like? And for each peak, they would have assigned a Miller indices, right? So the primary use of Miller indices is for material detection, and this is usually the procedure through which we find what material it actually is from some random powder or some random crystal. Do you get my point?
Yes, sir.
Yeah, I hope I was clear. Yes.
Yes, sir. Continue.
Yeah. Thank you. Thank you. So basically, if you know the Miller indices, you will know the material accurately. This is one of the standard characterization techniques. So next we will see the notation for the Miller indices. Okay. So usually, if a notation like this is given, you have to be very careful. In the problems, they will give different notations. So from that notation, you should understand whether this is a plane, or whether this is a direction, or whether this is a family of direction or family of planes. So okay, here also here also you have to see the difference. For lattice point and plane, it looks very similar, right? But here in lattice point, the points will be separated by commas, whereas if it is a plane, it will just be given without commas, but you will have opening and closing parentheses for both. Okay. If it is direction, crystallographic direction, you will be having a square bracket like this. If it's family of directions, you will be having this greater than or equal to greater than symbol or less than symbol. Okay. And if it's a family of planes, you will be having this flower bracket, right? In case there are any negative numbers, say 1 minus 1 or minus half, we will not be having minus in front of the numbers, so that will cause confusion. Instead, we will be having bar on top. Okay. So this is the procedure for finding out the Miller indices of the plane. First, what we do is we identify the intercepts on the plane. Okay. So usually there will be some problem given, like one say it will be like 1 comma 0 comma 0. So if something like this is given without any brackets or anything, we have to understand that these are intercepts. So from these intercepts, what we should do is usually it won't be 1 0 0. It will be like 1 in infinity infinity. So if it's like this, then we should take a reciprocal of this. Reciprocal means we'll be getting 1 by 1 comma. What is reciprocal of infinity? We know that it is 0 by 1. Infinity we know is 1 by 0, right? So reciprocal of infinity is 0 by 1, and here also 0 by 1. Then we have to clear the fraction. Clear the fraction means say 1 by 1 is 1. Sorry, no commas. Actually, 1 by 1. 0 by 1 we know is 0, and here also 0. Okay. We have to bring it to the lowest integers possible. Okay. And then finally we should enclose the numbers in bracket. Sometimes you will be having problems which will be like you'll have intercepts like 6 comma 4 comma 2. Okay. So in this case what we have to do is just take reciprocal. 1 by 6, 1 by 4, 1 by 2. Then we take LCM, okay, which is common for all these three. Number 6 is common, is it not? So on top, if 6 is common means we have to somehow
This is common, sir. It's
oh
not
yes,
6. 12 is the LCM, not 6, sir.
oh yeah, sorry, we have 4 over here, right? Sorry, it's 12. Okay. So after that what we should do is we should take 6 2s are 12, right? 2 comma this is sorry 4 3s are 12 and 2 6 are 12, right? So it will be 2 by 12, 3 by 12 and 6 by 12, and then after that it is 1 by 2 6 are 12, right? Then 1 by 4 and 1 by 2. Again we get fraction. Actually we have to clear the fractions. Clearing the fraction, so reducing the lowest integers. Okay, just a sec. Wait, first we'll go to the problems and we'll say. So okay, so here some of the example problems. So here what is given is we have the three what can I say planes. So here it is the 100 plane, right? Where in x-axis it is one. Say this is fixed as origin over here. So from origin this is at a distance of 1, and then when it comes to y or z, it is actually infinite. So what did we did as in the previous case, we took a reciprocal and then we brought the answer to 100, right? So if we find a 100 plane, it will most probably or always look like this. But if it is a 100 direction, it's a different story, right? So from origin, what we have to do is for directions, we have to take the second coordinate first. Here is 1. There is no other coordinates, right? In y and z direction. So it's 1, 0, 0 minus 0, 0, 0. Sorry. So if we minus these two, our answer will be 1, 0, direction, right? So 1, 0, 0 enclosed in square brackets. So that's how we get this particular direction. So if it is a 1, 1, 0 plane, then it will be like, usually the question will be 1, 1, infinity. So this is, say again origin is fixed over here, value of 1 is taken over here, right? And then y in y direction there is another one, so over here, and then z is infinity, right? So when we take reciprocal, we'll be getting 1, 1, 0. And another thing is, when it comes to planes like this, initially we will only be getting a line, okay? But then the thing is, this is just for a single unit cell. When you translate this to multiple unit cell, okay, you will be getting multiple lines like this. So what they usually do is, they will take this as the whole plane, right? That is why, you know, we get the image like this and not just a straight line. We take the full plane, the whole plane, whichever is considered. And since we are only considering one unit cell over here, it stops with this, okay? So we have 110 plane, then again 110 direction will be in this direction, because x 1 centimeter, say just x 1 unit, then y 1 unit, and then z no units, so it stops here. So 1, 1, 0 minus 0, 0, 0, which is the origin, we get 1, 1, 0 direction. Okay. So likewise, this can also be done. As I had mentioned earlier, the crystallographic planes will be like this. So it's not just a single unit cell. Rather, whatever the answer that we get for one unit cell, it will be translated across every similar unit cells. So from that we will be able to determine what type of material this exactly is. So here's another example. So again, this is a 110 problem. So these are the steps. First, we are given the intercepts like this. Then we will take the reciprocal, and then from the reciprocal, we'll reduce them to integers, and then finally we will get the indices. So again, this is another example. So yeah, here we are getting 1 by 2 as the intercept itself. So 1 by 2 means 1 by 2, and if you take a reciprocal of 1 by 2, we get 1 by 1 into 2 by 1, which is 2. So that's what we get over here, and then it is 1 by infinity and 1 by infinity. Usually the intercepts will not come in whole numbers. I'm sorry, intercepts won't come in whole numbers. It will usually come in terms of what can I say, quarters, or 1 by something, 1 by 6 or 1 by 4 or 1 by 2. The maximum intercept I believe is 1. So it's 0 to 1 only, not beyond 1. So the question itself in my case was wrong. So it will be like this, and then we'll have to take reciprocal, do the LCM and get the final value. Say in our case 642, we get 12. So 6, what do we do? 1 by 6, 1 by 4, 1 by 2. So we take reciprocal, we'll get 6, 4 and 2 directly, and from that we will have to like cancel. We will get 3, 2 and 1. So our plane will be like, sorry, just 3, 2 and 1. So for drawing this, what we can do is we can split, like say we have our cubic cell. What we can do is we can split. So the maximum is 3. So if we take origin over here, right, and x we have 3, so we can convert this in terms of 1, right? So from here we can take this as 3 parts, okay, and then number 2 we can take in y direction, which is lesser than 3. So this will be somewhere in the middle, half. Just a sec. Yeah. Oh wait. Where's the yeah. So this will be 2, and in the z direction it will be 1. So 1 part, 2 parts and 3 parts. So this can also be represented in this way. So it will be something like this, connecting these 3. So okay, yeah, here is a similar problem like that. So I hope you guys got this problem, right? So the intercepts are given like this: 1 by 2, 1 and 3 by 4. So we are taking reciprocals of this. We get 2, 1 and 4 by 3. Okay. Finally, we take 3, I guess 12, right? 12 or 6? 3. Yeah, I guess 3. 3 is common for, I mean, 3 is the only LCM like here. The other is just 1, right? So we take 3 common, and then 2 3s are 6. Sorry. Then 1 into 3 is 3. And then, sorry, write this again, just a sec, please. So 2 into 3, then 1 into 3, and 4. That's it, because there's already a 3 down here into 3. So these two get cancelled, and then you get 2, 3, sorry, 2 3s are 6, 3, and 4. So this is how we get our Miller indices. And then these are the family of planes. So if we take this 1, 0, 0 plane, right? It can, all of these possibilities that you see over here, 1 0 0, 0 1 0, 0 0 1, then negative, all of these will look exactly similar to each other. Okay, they will all be like, say, let's draw it. Okay, so we have a say a cube like this. Say this is the x, y, and z directions. So if this is 1 0 0, okay, then for 0 1 0, how will it be? It will be like 0 1 0 in y direction, right? This way, or sorry. So this is 0 1 0. This out. And then 0 0 1 will be over here. So likewise, if it's negative, okay, negative, what we have to do is we have to shift origin. Okay, so usually we keep origin over here. What we do is, if we encounter problems with negative, we have to first shift the origin over here. Okay, and from here, anything in this direction will be mentioned as x, and anything in that direction will be mentioned as minus x. So since one bar is negative over here, okay, and we have shifted the origin here, so this will be our 1 bar, this place, since origin is shifted here. If it is y of 1 bar, then what we have to do is, okay, this origin we have to shift to y negative. Which is y negative? This is y, like this is initial origin. We will shift to here. Okay, so if we keep 0 here, we can draw the arrow saying this is positive y and that is negative y. So if this is origin 0, then this is 1 bar in the y direction. Likewise, we can do for z. So if we do all of this, it will look very similar to each other. That is why they are all called a family of planes. Okay. Then directions we already saw, right? So what we have to do? So these are some of the examples. Okay. Usually here they have given directly, like they are the values are given, the intercepts are given. From the intercepts, we just take a reciprocal, and then after that we get the directions. But sometimes what will happen is, if two intercepts are given, say 10 and half, and say another 0 0 and another half is given, say two intercepts are given like this. In that case, what we have to do is, say let's take this is the point and this is origin. If something is like this is given, then what we should do is, we should do coordinate point. Coordinate point is this thing, okay, minus our origin. So 1 0 1 by 2 minus 0 0 1 by 2, right? So we'll be having 1 0 and 0. So this will be our final direction. Sorry, if it's direction, it's supposed to be 1 0 0. So this will be our final direction. In case 2 points are given, that is, and one is specified as origin. If something like that is given, then you have to do this. Otherwise, you can directly solve in this manner. Okay. So likewise, if negative is given, you should just take that as a bar. And for a family of directions, like family of planes, it is, as we saw in the greater than or lesser than symbols, right? Okay, now let's go for linear density. So so far, any doubts for anyone?
Sir, can you again show the page where all the notation of Miller indices were tabulated?
Yeah, just a minute, I'll show that. This one's right, yeah.
Yes, sir.
Sure.
Sir, for latest point is small bracket is to be given is necessary or not?
Which one?
First one, sir.
Yeah, lattice point. No, for point, yeah, it's better to give brackets. Yeah, but it's more than brackets, it's the comma that matters. I think if you don't give brackets, it will be considered as intercepts without brackets, because
Okay,
so
sir.
far
Okay.
everything that came without intercept was without brackets were called intercepts. Okay, usually for point, I think we have to put brackets. Plane also we should put bracket, but without the commas. So any other doubts?
No, sir.
Okay. Anybody else? Okay, we'll continue. So now we'll go to the linear density. So to find the linear density of atoms, okay, that is the number of atoms that are there along a particular line or vector. Okay, so that is called the linear density. It is nothing but the number of atoms in a particular unit cell. Okay, sorry, number of atoms along that particular line divided by the unit length of the direction vector. Okay, say for example, we have this, I mean the linear density of Al, okay, aluminum in 110, 110 direction. So we should be knowing that if it is aluminum, it is of a BCC type. So last time I think I would have shown you that tabular column, right? So in the tabular column, I believe it would have mentioned each.
Not BCC.
Yes. Sorry. What am I saying? This is FCC. What am I saying? Sorry. This is FCC. Yeah. This is not BCC. Sorry. This is FCC, because if it's BCC, you will have one central atom over here. Here, it's all in the faces. So aluminum is FCC. And to find the linear density, first we should check the crystallographic direction, right? We know how to find the crystallographic direction, no? So usually in the question they would have given this 110. So 110 means from origin. Okay, we consider some point as origin, and from that x-axis 1 and y-axis 1. So this particular point is the 110 direction point. They could have also drawn this down here, but then that would have been very messy, so they drew it up there. So no problem. It's our wish. We can take origin anywhere we want. Okay. So to find the linear density, what happens is we need to find the number of atoms in this particular line. So I believe from the diagram it is pretty obvious that like it is covering 2 atoms, right? So one atom over here, then these 2. So like from the midpoint of this to the midpoint of that, right? So we can consider that as 1. So we have 2 atoms divided by the length. So the length we obtain from the usual Pythagoras theorem. So this is A, that is another A. So your thing will be 2A square, right? And then finally you'll get root 2A. Let's say this is A, and let's say this is B, and let's say that point is C. So we want to find the value of BC square. Okay. So for BC square, it is AB square plus AC square. So AB square plus AC square is A square plus A square, which is 2A square, is it not? So for BC, we get root of 2A, right? Sorry. Yeah. This is the value of BC. And that length you write over here. And then the A value will also be given usually. So this is actually a gate problem. I forgot to mention which year it is. So this is a gate problem. I think somewhere around 2010 or something. So the A value is given, the lattice parameter, the direction is given. So from that, we should find out the linear density. So we should know what sort of crystal structure the particular material is, okay, and then we should do this particular calculation and get the linear density. So this is clear, right? Any doubts? Okay, I'll go to the next one. So now we have planar density of iron. So iron at so usually if iron 100 is given, so usually I believe it is BCC structure, right? So at temperature less than 912 degree, iron has its BCC structure. So for planar density, it is like a plane, right? And what is the formula for planar density again? The number of atoms of 2D, sorry, number of atoms of 2D repeat units. Okay, not 3D units, because we are dealing with planar. Planar is 2-dimensional. So the number of atoms in the 2D repeat unit divided by the area of atoms in the 2D repeat unit, right? So in our case we have the BCC, okay. So in BCC structure, if we would look at it from the side, it will be kind of arranged in a simple cube sort of format. So what we do is, from this we can draw a square, right? And then in this square we notice, I mean square as in this will be our unit cell, and in this unit cell we notice that 4 atoms are covered and a quarter of each atoms are covered, right? So it is 1 by 4 into 4. So the number of atoms in this unit cell is exactly 1 atom. So that is what is over here, and the planar and the area of the repeat unit is a square, right? So this is a square only, right? So it is a and area is a square. But to find out the a, we have already done the BCC calculation, right? So the answer was root 3a is equal to 4r, is it not? So the a value will be 4 by root 3 into r. So if we substitute those values, we will be getting the answer. How many atoms per nanometer square, or how many atoms per nanometer square or atoms per angstrom square? Anything we can get from this particular formula. Okay. Similarly, now we will go for the next one. So FCC with 110 plane, right? How will we solve this? Any idea? So I'll put a linear density formula. Linear density is number of what's this? Atoms in this unit cell, okay, divided by the, what comes here?
Area of the atom.
Area of the unit cell.
Area of the
Area of
unit cell.
atoms in it.
Yeah. So area of atoms in unit cell, right? So number of atoms here is, how many do we have?
Two.
Yeah, exactly. So we have 2. How did we get 2?
From the plane ABCDEF.
Yeah, from the plane. So what happens is, if we look at this plane, we have 4 corner atoms, right? So 4 corner atoms, and only 1/4 of the atom is in the plane. So 4 into 1 by 4 plus, we have 2 atoms in the faces, right? And each atom at the face is shared with the other atom, okay? Other unit cells. So we have 2 atoms into, each is shared by 2 unit cell. So we cancel, we get 2, right? 1 plus 1, we get 2. And then the area of the atom in the unit cell is actually, here it's like a rectangle, right? So anyhow, it's kind of like we can say A into A. So or we can, like, A into B, we can say, okay? A into B, and what we can do is
B,
in our, yeah,
B equal to A root 2.
yeah, and yeah, B value is A root 2, right? So finally we get our answer like 2 by A into root 2 A. So 2 root 2 A square, or we can even write it as root 2 by A square. So A value I have not given here, so we can conclude the answer like this. So next problem, you can try to do this as a homework. We'll discuss this next week. So you can take a screenshot of this and we can discuss this problem next week. You can try this as a homework. Okay.
Sir,
Yes.
B equal to A root 2. How, sir, in previous problem?
B is equal to A root 2, right?
Why,
So
sir?
here, like we see in this particular case, we have A. This we have, sorry.
Because AC is the diagonal of that cube.
Yeah, exactly. So we have AC now. AC is the diagonal, is it? So it the exact thing I'll let you know next week. Okay, I forgot like how. Remember the answer, but this I didn't know. Like I'll let you know next week. Okay. So next we'll go to the limiting ratios and structures. So the thing is, for every like identical shaped spheres, right? I mean, sorry, the atoms, the different radius, based on the different differences in radius, its arrangement will vary. Say for example, we have uh, for like hexagonal close pack and cubic close pack structures. Okay, the spheres will be almost equivalent to each other. The diameter, the radius of the spheres will almost be equivalent to each other. Say this is atom A of one element and this is atom B of another element. Okay, so they are, if they are almost identically sized, okay, they'll usually have this coordination number of 12 and they will usually be either HCP or CCP case. In case the difference in the radius of the atoms, okay, is in between 0.732 and 1, okay. So if the difference is, sorry, if the ratio is in between this particular range, then the cubic packing will be close to 8. Okay, the coordination number will be 8 and it will be of cubic structure. Okay, and then if it is in this limit 0.414 to 0.732, its coordination number will be 6. Okay, so likewise you will have different coordination. So here the coordination will be octahedral coordination. Okay, the others on if it's 8, it will be like cubic coordination. So if it is like 12, very close in diameter, means it will be usually HCP structure. CCP is like very rare, so it's usually HCP structure. Then next, this range 0.414 to 0.225 will be tetrahedral. Then 0.225 to 0.115, like if that ratio is there, then it will be triangular. Likewise, then it will be linear if it is very less. Okay, so you just remember this table, guys. So this you may get in your gate exam usually as 1 mark. Okay, so next we'll go for defects. Okay, so defects usually it doesn't make the material itself as defective, rather sometimes it makes defectives, but most of the times it will only give a better quality to the material. Okay, but there will be some sort of a difference in the material from its original structure. So first, if we take point defect, right, that is the first type of defect, we'll have some sort of a vacancy. Okay, some atom due to some process will leave the crystal lattice. So when it leaves the crystal lattice, there will be a vacancy created. So when that vacancy is created, okay, what will happen is, um, it's a hole, right? So the other atoms containing the electrons will try to come closer to it. So hole means it will be more positive, but these atoms will have electrons surrounding them, so they will be more negative. So what will happen is they will start coming closer together, and as a result, what will happen is, if a vacancy is created, it will usually be a compressive force acting on the bonds of the surrounding atoms. So what will happen is, usually when we do uh, processes such as diffusion or creep is nothing but you subjecting a particular material to repeated cyclic stresses for a long period of time. So if you subject it to creep and sintering, you will develop vacancies. Next, you have interstitial defects. So interstitial defect is formed when an extra atom occupies in a normally unoccupied site or interstitial site. So if you have a bunch of atoms here, then suddenly some atoms comes and sits in between the other atoms, right? Say when we are adding some sort of dopant or some extra atom, and it comes and sits over here, it will cause some sort of a repulsive force, because here also there are electrons, there are electrons, and then that will cause some sort of a repulsive force, and that will create what we call sorry, here is not a compressive force. This thing here is a tensile force. What is doing is, it is pulling all the bonds of the surrounding atoms. Here it is a compressive force, so it is compressing the bonds of the surrounding atoms. So this is a compressive force. Okay, then we have substitutional or substitutional defect. So in case of substitutional defect, it is similar to that of the vacancy. Like vacancy and interstitial, the only difference is that in substitutional, instead of the atom itself leaving, maybe a smaller atom will come or a bigger atom will come. If a smaller atom will come, again it will cause lattice tension, and if a larger atom comes, it will cause lattice compression. Okay, so when a smaller atom comes, the space becomes larger, no, the more space is here, and it is equivalent to half a hole sort of a thing. So what will happen is, it will start attracting all the nearby atoms closer together. Here if a large atom comes and sits, it will just repel the other atoms farther away, right? Then we have Frenkel and Schottky defect. Okay, so in case Frenkel defect, what will happen is, we will have a vacancy, usually an anion vacancy, and we'll have an interstitial pair. Can be anion or cation vacancy, and you will have an interstitial pair. Whereas if it's a Schottky defect, you will have only two vacancy, that is an anion and cation vacancy. Both will be missing in case of Schottky defect. Okay, so yes.
Frankel defect, explain one more thing.
Yeah. So in Frenkel defect, what will be there is, usually you will have one vacancy and one interstitial defect together. So that will be Frenkel defect. If it is a Schottky defect, we will have both vacancies, two vacancies, anion plus cation vacancy. So that is the usual difference between these two. Is it clear?
Okay, sir.
Yeah.
Yes.
So this is a usual formula for finding the interstitial defect pairs in case of Frenkel, and interstitial defect pair in the case of Schottky. But this is actually a rare question. This usually will not be asked in the exams. Then we have line defects. So definitely I believe there will be one question from this. So what will happen is line defects are usually one dimensional defects. Okay, line means we know it's one dimensional. So when we apply some sort of a tensile force, or when we add a set of a plane of molecules, okay, somewhere in the middle like this, what will happen is that will cause some dislocation in the surrounding atoms. So that is usually called line defect. Okay, so under line defects you have edge and screw dislocation. So if the defect happens along a particular plane, okay, it is called an edge dislocation, right? So say we are giving a we are introducing a new uh, plane of electron, sorry, a plane of atoms in here. So what will happen is it is causing a deflection. So that is called as edge dislocation. And then we have to always understand that the Burger vector and the edge dislocations are perpendicular to each other. So that could be a possible question. Okay, next. So this edge dislocation usually will be formed by tensile stresses or by the addition of a new plane of atoms. Next is we have screw dislocation. This usually will be caused by shear stress or like twisting action. So what will happen is only the upper front region of the crystal is shifted by one atomic distance and not a particular plane. So in this case the Burger vector and the screw dislocation are parallel to each other. Okay, also dislocation line and Burger vector, they both are perpendicular to each other. So this you just have to know. And I think we are out of time for today. So there is this last part called slip. Okay, slip direction, slip plane. So I think we will discuss this in the next class. So because it's already 7, is it? Yeah. So I'll just look into that previous lattice density, linear density once again, and I'll come back. And you guys can also work on that homework. And meanwhile, I'll also prepare that what do you call that notes for the gate exam. So thank you guys. Thank you for joining today. Yeah.
D?
Yes.
Sir,
Yeah.
any note or can share a PPT through Google Drive link, sir?
Yeah. That's what I said. Next week I will do that. Like I haven't started the drive, so I'll enter everything there. This drive, and also once I prepare the notes, I'll put it there. So you can
Also,
follow it from there. I will post that link next week for sure.
this session recorded is available.
Recording, I don't know whether I can give, because it is like usually goes to that NPTEL gate portal.
So some lectures share the YouTube link.
Yeah, then I'll do that. Yeah, I'll do that. I'll create a small YouTube channel. So
Okay,
I'll
sir,
just
thank you.
upload these lectures there, and I will share it with you guys.
Okay, thank you, sir.
Sure.
Okay, sir. Thank you, sir.
Thank you so much, guys. We'll meet next week. Yeah.
Bye,
Okay,
sir.
sir. Okay.
Uh,
Thank you.
thank you, guys. Bye bye.